Dear learners, in this video, I am going to explain you the interior of the earth or earth's interior. As you know that our knowledge of earth's interior comes from analyzing surface features such as road cuts, landslide scars, volcanic flows and the stratigraphy of deep canyons. Scientists also gain information from seismic waves that travel at different rates through the interior layers of the earth. When scientists analyze these different sources of information, a clear picture of Earth's interior emerges. The structure of the interior also reflects the processes that formed our planet. So firstly, in this video, I am going to explain you why does Earth's interior have a layered structure? As you know, along with the other planets and the sun, Earth is thought to have condensed from a nebula of dust, gas, and icy comets about 4.6 billion years ago. As Earth solidified, gravity sorted materials by density. Denser substances such as iron gravitated slowly to its center, and less dense elements such as oxygen, silicon, and aluminium slowly welled upward to the surface and concentrated in the crust. Consequently, Earth's interior is sorted into roughly concentric layers, each one distinct in either chemical composition or temperature. Thus, Earth's core is nearly twice as dense as the mantle because it is composed of denser metallic iron nickel alloy. Dear learners, as you know, that at Earth's center lies the dense metallic core and it has been divided into an inner core and outer core. The core makes up one third of Earth's entire mass, but only one sixth of its volume. The inner core of solid impure iron is well above the melting temperature of iron at surface conditions, but remains solid because of tremendous pressure caused by the weight of the overlying materials. The outer core is molten iron and has a lower density than the inner core, and this is the only layer in our Earth's interior that is in liquid form. The rotation of Earth affects the fluid outer core, generating Earth's magnetic field, and you know that the magnetosphere surrounds and protects Earth from solar wind and cosmic radiation. A compass needle also points to magnetic north because of Earth's magnetic field. Above the core lies the mantle, a layer of hot but mostly solid material that represents about 80% of Earth's total volume. The mantle is rich in oxides of iron and magnesium and in silicates, silicon dioxide, a component of many rocks and minerals. The extremely high temperature and pressure in the lower mantle softens and deforms solid rock material over millions of years. Just as boiling water in a pot rises to the surface, rocks in the warmer lower mantle rise upward where they slowly cool as their heat is transferred to the upper mantle. As the rock material cools, its density increases and the rocks begin to sink and move downward, also aided by gravity. The up and down movement of rock material in Earth's interior is the result of these convection currents which power the process of plate tectonics. Dear learners, now I will explain you the characteristics of the asthenosphere. Asthenosphere is not the layer that has been classified based on its chemical composition, but it has been classified because of its behavior and physical properties. As you know, in the upper mantle, closer to Earth's crust, the temperature and pressure decline. So the rocks are more rigid. The asthenosphere lies just below the lithosphere and extends from about 70 km beneath Earth's surface to a depth of 250 km. The asthenosphere is the least rigid part of the mantle. Geologists describe the rock of the asthenosphere as being plastic. This means that its weak material can bend or flow slowly over long periods of time. The asthenosphere contains pockets of increased heat from radioactive decay. This partly explains why about 10% of this layer is molten in uneven pattern and hot spots, and why slow convective currents occur in its hot plastic material. The resulting slow movement in the asthenosphere disturbs the overlying crust and creates tectonic faulting, and deformation of surface rocks. Above the asthenosphere, the uppermost 70 km of mantle and Earth's crust are collectively called the lithosphere. This layer floats on the asthenosphere and is broken into plates that are moved during tectonic processes. The Maharovicis discontinuity or MOHO separates the crust from the mantle. The MOHO is named for the Croatian scientists who determined that seismic waves generated by earthquakes change at this boundary because of the change in earth materials and densities. Above the MOHO lies the crust, Earth's rocky outer shell made up of the continents and the rocks that form the bottom of ocean basins. The crust represents only a fraction of Earth's overall diameter and varies in thickness. Crustal areas below mountain masses are 50 to 60 km in thickness. Crustal areas beneath continental interiors are about 30 km in thickness. Oceanic crust averages only 5 km. The average thickness of continental crust is 35 km, but in mountain ranges, the thickness of continental crust is about 60 km. Its composition is granitic or felsic, and average density is 2.7 grams per cubic centimeter. Continental crust is made up of many different types of igneous, metamorphic, and sedimentary rocks. The average composition is granitic, whereas oceanic crust is 5 to 12 km thick. Its composition is basaltic or mafic. Thin layer of unconsolidated sediment cover basaltic igneous rock, and the average density of oceanic crust is 3.3 gram per cubic centimeter. Dear learners, one thing keep in mind that oceanic crust has also layered structure consisting of the following: pilobasalts, basalt that erupted subaqueously; sheeted dikes, that is interconnected basaltic dikes; and gabbro, coarse grained equivalent of basalt cooled slowly.